All right, so in our last video, we covered the mechanism for converting an aldehyde to an acetal or a ketone to a ketal. And as we saw, the mechanism was pretty steppy, but ultimately in the end, we're able to add two equivalents of alcohol to the carbonyl to form our ketal or acetal. Like I said, you can favor formation of the ketal or acetal by driving the equilibrium to one side or the other by removing products, in this case by removing water, or by flooding the reaction with starting materials. So for example, using excess alcohol. All right, what I want to do next is kind of a variation on this, and I apologize, again, it's going to be very steppy. And this involves forming cyclic acetals or ketals. And I'll show you why this is useful, but let's first just practice the mechanism. So again, I'm going to use acetone as my generic ketone. Again, it'll work with aldehydes. But instead of using two different alcohols, I'm going to use a diol. So in this case, this is ethylene glycol. It's a common commercial alcohol. It's used in a lot of products. And same idea here. You don't need two equivalents of alcohol because you already have two alcohol groups. And we're going to treat this with catalytic acid. Okay, so first step will be to protonate the carbonyl. This will make that ketone or aldehyde really electrophilic. And then in your next step, your alcohol, at least one of them, can add in and kick up electrons to that oxygen. All right, so let's take a look at what happens next. And I'm going to zoom out a little bit, give us a bit more space. When this happens, you'll have an OH group, and then you'll have one end of your alcohol kind of hanging off here, but that proton is going to be still on that first oxygen that attacked in. So what I mean by that is this proton is still on there. So we want to show removal of that proton. So let's go ahead and show that. So I'm just going to write minus H plus to say that we're removing this proton. And when we do that, we'll get a neutral intermediate. And if you remember, this is called a hemi-ketal, meaning the alcohol has only added in once. It's halfway to our product. All right, so let's imagine what could happen next. Well, we've still got our acid around in solution. So in the next step, what we're going to do is we're going to add that proton right back in, but at a different site. So just like before, we don't want to add it right here, otherwise we'd be going backwards. So instead, we're going to protonate this alcohol and convert it into a good leaving group. So in many ways, this is very similar to our previous reaction that we covered, where we convert this into an amazing leaving group. And if it's a leaving group, we can then go ahead and nudge this off. All right, so I'm going to slide everything down because clearly I haven't given myself enough room. And then let's take a look at the intermediate that's formed after we kick off that leaving group. So at this point, we'd have an oxygen with a positive charge, and water will have been ejected off. So this was our leaving group that was ultimately ejected off the molecule. All right, so now the question is, well, what do we do at this point? Well, we still have this alcohol right here, and that alcohol can actually attack into the carbonyl itself. So what happens if we do this? Well, we can kick electrons up. And when we do that, we're going to form this weird ring system. Let me slide this over, I guess. We'll keep things in the same spot. Sorry, this is the easiest thing to draw. But there we go. So this alcohol right there is now at this position. It's kind of attacked into itself. And we also have water floating around. That was the water that was our leaving group in that previous step, right? All right, so the last step for this reaction is just going to be a simple proton transfer or deprotonation, where you show loss of that proton. All right, and what this is called is a cyclic ketal. If you do it with an aldehyde, it'd be a cyclic acetal. But the question is, why might this be useful? It doesn't seem to be any different than the previous reaction. Well, I'll show you why this is useful. It's a cool trick. Let's consider this overall net reaction. Let's say we've got acetone, and we treat it with our ethylene glycol under acidic conditions. What you can do is isolate your cyclic ketal product and get water out. Oops, sorry, this should be acid catalyst in between. All right, so this is the net reaction. So like I said, we can get this reaction to go one way, meaning we can drive it to a product formation. So what I'm going to do is I'm going to block this out, and I can say, all right, let's do the forward reaction. And so in order to do the forward reaction, we're going to use the same reagents. But this time what we're going to do is we're going to say H plus is catalytic. And in order to get this out of equilibrium condition, we're going to remove water during the process. So I'm going to write minus H2O. And really what this means is that water is removed during the reaction. All right, so maybe it's distilled off or absorbed into some sort of absorbent. Doesn't really matter as long as it's being pulled out of the reaction mixture. And when you do this, if you're pulling water away, you can drive the equilibrium and favor exclusive formation of your product. So this is really useful. The reason that this is useful is essentially this entire group right here acts as a protecting group for ketones or aldehydes. For ketones or aldehydes. So if you think about this, this product that we've made, will it react with the Grignard? No. Will it get reduced to an alcohol? No. It won't do any of the traditional chemistry that aldehydes and ketones normally do. All right, so that's great, but the question is, protecting groups are only useful if we can take them off at the end. So let's imagine the reverse reaction. And the reverse reaction would essentially be deprotection. All right, so let's consider this reverse reaction where we have this protecting group on there. And now we want to get this protecting group off. Well, if we want to get the protecting group off, we should go back to the parent reaction and say, all right, our goal is to go from here over to this side, right? So how can we push that equilibrium? Well, a simple strategy would be to just flood it with a ton of water. If you flood it with a ton of water, Le Chatelier's principle says it'll favor the opposite side of the equilibrium. All right, and that's exactly what you can do to deprotect. So you react this with H2O in excess, and then treat this with catalytic acid. And when you do this, you can go in the complete reverse reaction, and you can kick off that alcohol as your leaving group. So this allows you to deprotect your protected aldehyde or ketone. So let's see this in context, because sometimes a lot of these examples don't make sense unless you see it in a reaction. All right, so let's do an example reaction. In this example reaction, I'm going to have a ring with a ketone, and then I'm going to have an ester over here. And my goal is to convert this starting material into this product where the ketone is still present on the ring, but the ester has been converted to a primary alcohol. When I look at this, I realize really quickly I've got a ketone there. And if I tried to treat this with LAH to reduce that ester, followed by water, the ketone would actually be more reactive than the ester. So if we did that, we would end up with an alcohol here and an alcohol here. This is not wanted. So the question is, how can we get around this problem where LAH would reduce both the ketone and the ester? Well, what we could do is we could first protect the ketone. So in order to do that, I would treat it with ethylene glycol. I would treat it with my catalytic acid, and then I would remove water from the reaction system to drive this out of equilibrium. All right, so when I go ahead and do this, I'm going to get this 5-membered ring. The ester will not form any sort of product with ethylene glycol, so it'll just hang out. This reaction where you form a cyclic acetal or ketal only works with ketones and aldehydes, not esters, carboxylic acids, amides, anything like that. All right, so now at this point, we've got things protected. I can treat this with LAH and then treat it with water to work it up. The protecting group is just going to stay put. It's not going to do anything. But this ester over here will react with LAH. So this will give us the reduced ester, which gives you a primary alcohol. Now what we need to do is we need to remove this protecting group to get to our final product. And to get to our final product, all we need to do is treat this with excess water and then treat it with catalytic acid. And by doing that, we can pop off that protecting group and get to our final product. So this is a pretty clever protecting group for aldehydes and ketones. All right, so that's where we're going to stop right now. When we come back, we'll take a look at nitrogen nucleophiles rather than oxygen nucleophiles.